welcome to this. I think it's probably going to be the last NITheCS seminar for this semester. Oh, it depends if we get a resident. But welcome to this seminar, and I'm glad to see that these seminars are gaining traction. We're having them more regularly, and we're getting a reasonable turnout. So today our talk is going to be more in cosmology, and the speaker is Dr. Pankaj Kumar. He's from a university which has a very interesting name. I think you would take affinity with that. You know that name, and you've shown great taste in using that name. Dr. Pankaj Kumar is an associate professor at this nameless university, and it's in a very beautiful part of the Western Himalayas, in Shimla. Nearby, close to Shimla. It's a very beautiful city, a beautiful town, a British creation, and it was set up as what Indians call the hill station. Yeah. I think that was an attempt by the British to avoid the heat, the summer heat. Oh, and it's certainly cooler. So Dr. Pankaj Kumar is a research visitor officially at the University of Zululand, but he's based also at the University of KwaZulu-Natal. And his formal host is Professor Arun Bishop, who is, people seem to be moving around a lot. So the University of Zululand, but now he's based at Nangasuthu University of Technology. He's willing to accept salaries from multiple sources. So that's it. So Dr. Kumar, not associate professor, so Professor Kumar, he's visiting for 6 months. Yeah, 6 months. And we're glad that he's made himself available to make this presentation. So over to you, Pankaj. Thank you.
Thank you, Professor Sunil. And thank you for all. And thanks to NITheCS for organizing this webinar. And Professor Maharaja always forget to get his name after my name, that we are doing research collaboratively with Professor Agrasen and Professor Maharaja. And he is my official supervisor, caretaker in the university. So today we will discuss about the standard model of the universe, its problem, and beyond it. What are the things going beyond this model? What we are discussing beyond this model? This is a picture of my university, Professor talking about. It is in the foothills of Himalaya. There are the 3 ranges of Himalaya: lower Himalaya, middle Himalayas, and upper Himalayas. So this is near the lower Himalayas. The university name Maharaja Agrasen University. Don't get confused with Maharaj. This is Maharaja. So let's start with some very basic and important things. What is the source of our knowledge? Source of our knowledge about universe. Definitely it is the light. Either we are observing things by our eyes, or we are observing by the telescopes. And we are getting nowadays very refined telescopes like James Webb we are having presently. So light is the main source of our knowledge. If there is no light, our knowledge will be very limited. Then other way to get knowledge is either we will hear, or by the touch, or using the smell, but that will be the very limited, very limited. Light is the only main source of information about everything. So the speed of light 2.99 multiplied 10 to the power 8 meter per second. Looks very fast. Light takes just 0.13 seconds to go around the Earth. Even less than the 1 second takes time. And it takes just 8 minutes 20 seconds come from Sun to the Earth. So wow, light is extremely fast. But this is not the case. This is our galaxy, Milky Way. This is 100,000 light years across. 100,000 light years. It means light takes 100,000 years to cross our single galaxy. And this is the picture without adding dark matter. This is the picture without adding dark matter. If we consider dark matter, it's more than 10 times bigger than this one. So if we see at the larger scales, light is very, very slow. We seem to be very, very fast on the Earth. And we have discovered billions of galaxies in our universe. So you can imagine how large the universe is and how slow the speed of light is. And that is the only source of information we have. Some most interesting objects of the universe, black holes. So black holes are the objects where curvature of space-time becomes almost infinite. That means the gravity will be almost infinite at that point or at that region of the space. And currently, there are only 50 confirmed or suspected black holes in our galaxy, Milky Way. But astronomers and scientists thinking that there may be 100 million of black holes in our own galaxy. Look the comparison between 50 and 100 millions. So we know the information, our knowledge about our own galaxy also is very, very limited till now. Very recently, I read in the news, I think 15 days ago, we have discovered nearest black hole to Earth, which is 2000 light years away from the Earth. This is the nearest discovered black hole to the Earth. But there may be some other one which are sitting very near, maybe 100 light years away from us, maybe 20 light years away from us. We have not discovered because we are suspecting that there are 100 million maybe black holes in our own galaxy. If we talk about the inverse, there may be millions of billions of black holes. So universe is mind-blowingly large. It may be too large, we can't imagine how large it is. Our knowledge about the universe is less than 1%. We see that our knowledge about our own galaxy is not too much. Maybe billions of black holes and we are just found only 50 out of millions. We are seeing very old picture of the universe because the speed of light is limited. It looks very fast on Earth, our local sounding, but it is very, very slow on the universal scale or cosmological scale. So the picture we are seeing about the universe is very, very old, and we will never be able to see the present picture of the universe. Suppose someone sitting on the other side of the galaxy and I am giving talk here and I want to deliver this talk to that person, and I send signal to that person, it will take near about 80 to 90,000 years. Maybe thousands of generations have passed of that person. Then that generation will see this presentation there. So these are some limitations we have in, and this is our situation about the universe. So let's go to the main topic, the standard model of the universe. Let's understand this model using this picture. This is the very recent picture. The older picture of the standard model was not like that. Here we are, this model is starting with a bang called Big Bang. The name Big Bang was coined by Sir Fred Hoyle in a BBC interview in 1950. After the Big Bang, we observing an accelerating phase of the universe called inflation, and after the inflation, we observe a decelerating expansion of the universe. And at the same time, we observe again another accelerating expansion of the universe. But if you see, before 1981, the picture was different. There was no inflation at that time. There was just Big Bang, and after this bang, there was a decelerating expansion of the universe. Universe is supposed to be decelerating. But because this model having some problems like flatness problem, monopole problem, to resolve that kind of problem, the inflation was proposed by Alan Guth in 1981. After 1981, the inflation was added in this standard model of the universe. And the last one, the accelerating phase of the universe, was added after the discovery of accelerating universe in 1998 by two teams, Rees and Perlmutter. Separately, they discovered that universe is accelerating based on the observation of supernova. So this picture of the universe, or this model of the universe, is based on general theory of relativity. And the model is known as Lambda-Cillian model. We will discuss later. So the main established theory about the evolution of the universe till date is the general theory of relativity. So what we can understand this theory by this picture very well. This is the sun, this is the earth. So this picture telling us that the heavier the mass we have in, the large curvature of the universe we will see. Like if you want to observe simply, you just take a bed sheet and tie all the four corners and put some mass on this, then it will be curved. That's why this is the fabric of space-time getting curved by the mass, or you can say energy. This is the earth. This is also making this space-time to curve, but not like that. We are seeing for the sun, because sun is more heavier than the earth. So very famous statement of Wheeler about the space-time. Space-time tells mass how to move, and mass tells space-time how to curve. Field equation of Einstein using the general theory of relativity. The first equation is original field equation, proposed by Einstein in 1915, and I think published in 1916 or 17. R mu nu Vicky tensor minus 1 by 2 R. R is a key scalar. G mu, this is a metric tensor, equals to 8 pi G over C to the power 4 T mu. T mu is the energy part, energy momentum tensor. The right hand side represents the energy part of the field equation and left hand side represents the geometric part of the universe. Somehow Einstein connected these basic property of the universe, geometry of the universe with the energy of the universe, and proposed the general theory of relativity. After that, Einstein modified field equations and introduced the cosmological constant lambda. The main purpose to introduce this cosmological constant lambda was to make the solution static. When he solved his equations, he observed that solution is non-static. At that time, he supposed to that universe is static. Even everyone supposed to that our universe is static. That's why to make the solution static, he introduced the term lambda. Because his equations allowing this term to introduce. So he thinks that we may introduce lambda and he obtained a static solution from it. A big change in our understanding came in 1998 when we observed that universe is oscillating. But the problem is that from where this oscillation is coming, what is behind this oscillating universe? The term being used to oscillate this universe is known as dark energy. Because we know everything, somehow it is energy. Either it is a matter or whatever it is, everything is energy. So this is nice to say that like energy. So because you don't know, so that's why we are saying this is a dark energy. And the cosmological constant Einstein proposed to make the solution static came in picture again. Now this same cosmological constant now is able to oscillate the universe. And this model with lambda and cold dark matter CDM is known as the standard model of the universe. The cold dark matter is also required to explain some galaxy formation and their stability. It is required, so it also comes in the picture. So combinedly, this model is known as lambda CDM. Lambda is the cosmological constant. The model is very predictive and robust observationally, but this model nowadays facing some serious problems. So let's discuss about the problems this model facing. So there are three main problems which the model is facing. The one and very old problem is fine-tuning problem. Second one is the age problem, which is also a not old, but this is new also, and as well as old also, but very new and very intense problem the model is facing is H-naught tension. So let's discuss what are the problems. Fine-tuning problem. Lambda is supposed to be the energy of quantum vacuum. And the observation value of this quantum vacuum and theoretical value of this quantum vacuum having a difference of order 10 to the power 60 to 10 to the power 20, which is very, very large and which is not acceptable in any limits. So this huge difference is known as the fine-tuning problem or cosmological constant problem. The model is this. The second is the age problem. The age of the universe, according to lambda CDM model, is coming out to be 13.8 billion years. But we have observed some objects in the universe itself which having age more than the age of the universe itself. How it is possible? The oldest star in the universe is found to be 14.27 billion years old. The name of the star is HD 140283. In a very recent paper in the Astronomical Journal published in 2023, they have found a star cluster within our galaxy Milky Way having the age 13.80 plus minus 0.75 billion years. If we add the upper limit, then it becoming the more than age of the universe. It means the prediction about the universe by the lambda CDM model is not correct according to this level. So this problem is known as the age problem. Some objects inside the universe having age more than the universe itself. And the major problem nowadays, there are lots of talk about this problem among the cosmologists and astronomers, S-node tension. So let's understand what the S-node tension is. CMB, cosmic microwave background, means very old universe. When the universe was opaque and the light was able to move around, when the universe was just less than 1 billion years old, depending on that type of universe, Planck was the mission which was totally dedicated to CMB. Using the Planck's data, lambda CDM model predicting the value of Hubble constant, which is 67.4 and plus minus 0.5. But using the local measurement means very young universe, or the supernova we are observing nearby. From there, we are getting the value of S naught, which is 73.03 plus minus 1.04. And the Nobel laureates A.G. Rees have published paper on this. So difference between these two, the older universe, the value of H naught we are getting from the older universe, and the value of H naught we are getting from the younger universe, the difference between these two values is more than the 2 sigma error, acceptable 2 sigma error. 2 sigma error is acceptable because there may be some statistical error or maybe some observational error. But beyond this error, we cannot accept the errors. But this error between these two, difference between these two values is more than 2 sigma. I think it's near about 4 or 5 sigma. So that's why this problem is a major problem, and in a very recent paper, Rees have discussed clearly that this problem is a problem. Before that, we are thinking this may be due to some observational problem or statistical problem, but they are clearly mentioning that neither the statistical problem is there nor the observational problem is there. There is a serious problem really between the older one. We are missing something between the older and between the younger universe. And very recent data from DESI. DESI not any poor girl. DESI dark energy spectroscopic instrument. Very recent instrument dedicated to dark energy. The first observations of this DESI is saying that dark energy is dynamical. And even this data is saying that dark energy is weakening. Means we may observe this relative universe in future. But this is the just first observations. Let's see what happens in next installment of observations. But first year observations from this survey indicating that dynamical dark energy at the place of a cosmological constant lambda. For more detail about the problem with standard model, you may go to this review paper published in New Astronomy Reviews in 2022. So there are other problems with lambda-Schedian model, not only these three problems. So what are the alternatives we have? So basically we have two types of alternatives, either modify the theory, known as modified theory of gravity, and the framework is same as of GR. We are just modifying this framework in some way to get rid of that kind of problems. And as Deji is saying, the other part is dynamical dark energy models. We have to choose some dynamical dark energy models on the place of cosmological constant lambda. Like many authors have discussed time varying cosmological constants. Chaplin gas also a dynamical dark energy candidate. Holographic dark energy, baroholographic dark energy, near-graphic dark energy, ghost dark energy. There are too many depending on the different kind of source from where they are coming, according to which they are different. And we have so many modified theory of gravity. One of the famous modified theory of gravity, FR theory. Other is FRT theory, Einstein Gauss-Bonnet theory, also very popular, and Brans-Dicke theory is also a natural extension of general theory of relativity. And combination of above these two ideas is also popular in the literature. Researchers doing dynamical dark energy models in the modified theory of relativity. The purpose is one, we want to explain this universe in more better way. When we find the problems, solution of the problems we having with lambda-Schedian, that is the main purpose. So motivated by these, we have discussed a model, baroholographic dark energy in FRT theory. So let's see what is the baroholographic dark energy. Baroholographic dark energy is modification of holographic dark energy. And holographic dark energy is based on the holographic principle proposed by Keyhout in 1993. This principle tells that we can study a three-dimensional object using the two-dimensional property. Like we can discuss the property of a sphere using the surface area of the sphere. Using this principle, the holographic dark energy was coordinated. To get the energy density of this holographic dark energy, Bekenstein-Hawking entropy was used, and the energy density of this holographic dark energy was given by 3c square and p square n to the power minus 2, where c is a constant, mp is the reduced Planck mass, and L is the infrared cutoff. Infrared cutoffs are the related to the longest distance in the universe. So baroholographic dark energy has been obtained by replacing the Hawking-Bekenstein entropy and replacing by the baro entropy. Hawking-Bekenstein entropy was replaced by the baro entropy, and the modification of holographic dark energy obtained as a baroholographic dark energy, which is given by question number 3, where delta is coming from the barrow correction to the holographic dark energy. And this delta lies between 0 to 1. In the present study, we consider Hubble horizon as the infrared control. So when we use this value, then we get the energy density by equation number 4. The action for FRT gravity. In the general theory of relativity, we have R here as the place of function of RT. If we put R at the place of FRT, then we get the action for general theory of relativity. So, general theory of gravity is being modified using the function of R and T, where T is the place of any energy momentum tensor. The G is the determinant of metric G mu, R is the Ricci curvature scalar, Lm matter Lagrangian density, and P is the trace of energy momentum tensor. We consider a flat Friedman Robertson Walker space-time given by equation number 6, where A denotes the scale factor of the universe. We consider a very simple form, a linear form of FRT, which is given by R plus alpha T. Varying the action 5 using this metric 6, we get the field equation 7 and 8. Now our motive is to solve these two equations to find the value of H, Hubble parameter. So if we combine these two equations 7 and 8 using the equation of state, barotropic equation of state, pH equals to omega H to H, we get the equation number 9. So this is a single equation, and it is a differential equation. But problem is, we know the value of rho H, but here we don't know the value of rho M, energy density of dark matter. So we have to find the value of rho M here if we want to solve this equation number 9. And we can find the value of rho M from equation number 7. So using equation number 7, we obtain the value of rho M given by equation number 10. And now using the value of rho H, energy density of barrow holographic dark energy we discussed, and using the value of rho N, we get a single equation given by equation number 11. So here if we put delta equals to 0, which is coming from the barrow entropy, the entropy converted into the Hawking-Bekenstein entropy, and we get the energy density of holographic dark energy. And holographic dark energy has been solved in the FRT gravity. So for the case lambda equals to 0, we get the holographic dark energy which has been discussed. So here, to solve the equation, we consider a maximum distortion from the Hawking-Bekenstein entropy, which is given by delta equals to 1. This is the maximum distortion to the Hawking-Bekenstein entropy. So for delta equals to 1, we obtain the equation 12, which is a differential equation, linear differential equation in H, and very easy to solve. Solving this equation, we can find the value of H very easily. So we solve this differential equation and obtain the value of H given by equation number 13, which is coming in terms of T, time. Here T naught represents the present time and H naught represents the present value of Hubble parameter. Again, using the relation H equals to A dot by A, we can easily find the value of scale factor A for this value of H. This is the value of scale factor A we obtain, and then we convert the value of H in terms of Z. Because the Z is important because the later time of history of the universe is very well known in terms of Z. we know at the what value of Z, the phase transition we observed, and so many things of the inverse we know very well in terms of relative parameter Z. That's why it's important to write the quantity in terms of relative Z. Now we have obtained the value of scale factor A, then we can find value of Q, which is directly coming from the value of scale factor. We know the formula of Q in terms of A. Using value of scale factor, we can find value of Q, which is coming like in equation number 16, and then we obtain effective equation of the state, which is given by equation number 70. In terms of relative parameter Z. Now the part of this research, let's estimate the model parameters using the available observational data. So we have used two combinations of data here, and in the next one we will use added another one using the three data. So here we are using the Pantheon plus supernova data, very recent, and the observable Hubble data to plot these contours. And we have used MCMC, Markov and Monte Carlo, and EMCE Python package available to plot these contours. So we are observing the value of the model parameter C, which is coming in the energy density of baroholographic dark energy, WH equation state of baroholographic dark energy, alpha is the parameter coming in the home, R plus alpha T, and H naught is the Hubble present value of Hubble parameter, and this M is used in the supernova calculations. So this M is coming from there. Interestingly, if you observe the value of alpha at the 2 sigma confidence level, the value alpha equals to 0 is excluded. For alpha equals to 0, our model, baroholographic dark energy model in FRT gravity converted into baroholographic dark energy model in GR. But alpha equals to 0 is excluded in the 2 sigma level, confidence level. It means the observations are preferring or preferring the FRT gravity over the GR as far as the Brans-Dicke baroholographic dark energy is concerned. In the next one, we add another data from Su collaboration, and we observe here also the case alpha equals to 0 is excluded at 2 sigma confidence level. And we have obtained the value of H naught, omega HC using this combination of observations. So these are the best fit value we are obtaining using the two different combinations of observations. The main thing is H naught. As we are adding the observation of Su, we are observing a significant change in the value of H naught. Now, this value of H naught is coming near to the value model in independent way have obtained by the resetter, which is near about 73 point something. And you can say this value is in between the value of old universe and in between and the new universe. The old universe we are having 67 point something value, and from the old old universe the value of H naught was 67 something, and from the younger universe, the value is 73 something, and this value is coming in between both. So somewhere we can say that the model is able to reduce the H0 tension in some way. Not exactly, but some way it is able to reduce this H0 tension of the lambda CDM model. This is the Hubble parameter plotted for the lambda CDM model and both the combination of observations. We see for both the combinations in the past, the evolution of this Hubble parameter very different from the lambda CDM. But in the present, it's becoming almost same, but the second combination is providing the higher value of H0 in comparison of the other two, which is significant. Which is able to explain the H0 tension in some way. This is the well-known deceleration parameter as the observation of 1998 showing that our universe is accelerating. The model is showing acceleration. The phase transition from decelerated phase to accelerated phase, we are observing near about the Z equals to 1, which is observationally acceptable region of the phase transition. And in the future, we are having the negative value of Q, showing that in future, our universe is going to accelerate, like lambda CDM model also predicting that we will have accelerated universe in future. But the second combination, when we use collaboration data, the transition occurs early in comparison to the other one, as we are having a large value of H0 here. This is the effective equation of state in the similar way. Definitely the second one turning the early because this predicting the phase transition early. So the effective equation of state become negative earlier than the first combination. This one, and in the late time it's going to -1. And -1 refers to the lambda CDM model. The equation of state of lambda CDM is -1. This is the age of the universe. We have plotted for the lambda CDM model, which we know is 13.8 billion years. And for the first combination, we are having near about the lambda CDM model, but the significant change is the second combination as we add the data from collaboration. We having age more than 15 billion years. And this is important because in this model, we can accommodate the oldest star having the age 14.25 billion years and the cluster we having in Milky Way having the age of 13.80 something plus minus. In this model, as we are having 15 point something, the age of the universe, we can accommodate these ages very well. So this model is able to get rid of the age problem of lambda CDM. This is the state 100 analysis. State 100 analysis is used to compare dark energy model with the other dark energy models, how your model is behaving. So if we see the trajectory starts from the negative value of S and positive value of R. This is behavior like 20 cents used to behave. Sorry, not 20 cents, Chaplin gas. Chaplin gas behave like negative value of S and positive value of R. So in the starting, the model start like behaving like Chaplin gas, and it's go through the lambda CDM model, which has value 1 and 0, 1 value of R and 0 value of S. And after that, you see that the R and S both having the positive value. So this, after the lambda CDM, it's behaving like a 20 cents model. So in the late time inverse, R model is behaving like a 20 cents model. This is the Ohm analysis, and the same thing, the Ohm analysis is also saying that in the late time we having the negative slope of the trajectories, and it's behaving like a 20 cents in the late time evolution. So the result analysis about this model. The model is able to explain the late time evolution of the universe, oscillating universe. The model provides the values as noted is 70.44, which is close to the model independent value is 73.5 obtained from the local measurements. Thus, the model reduces the H0 tension we having with the lambda CDM model. The case alpha equals to 0 is excluded at 2 sigma confidence level, i.e. the recent observations are favoring FRT gravity over general relativity as far as zero holographic darkness is concerned. Because we will, if we put alpha equals to 0, then this model will convert into the zero holographic darkness model in general theory of relativity. The age of the universe we obtained using this data, combination of 3 observations, we obtained value of age of the universe is 15.43 billion year. Both are the same. So we can accommodate the star cluster M92 observed in our galaxy Milky Way, is having the age more than the age of the universe itself. So we are easily accommodate in our model, and the oldest star which having the age 14.5. So thus the model resolves the age problems. So thank you for listening.
Thank you very much for that, Mr. Pankaj. The broad overview. It's very helpful for students and people outside the area. Are there any comments or questions?
Just a comment. You know those black holes which you mentioned, those are the stellar black holes, right?
Yeah.
And then apart from that, you also have your primordial black holes.
Yeah.
And then also, you know, supermassive black holes, which are believed to exist, you know, at the center of the galaxy.
Definitely, they are stellar black holes I'm talking about.
And they are very massive.
Yeah. Supposed to be sitting at center of every galaxy.
Can I ask a question? You know, you talk about this fine-tuning problems, age problems and all of that. You're getting a difference between theoretical predictions and observations. Now, in your, is that really a problem? Because the situation is that our observations are so limited that, I mean, how seriously should we treat it? Because as time passes on, those observations may actually tend towards predictions. Or do you think that they will diverge?
Like there is a way to find the theoretical value, because we know how much the energy the one part of the empty space can have. So according to these calculations, the physicists have found the value of this quantum vacuum. So this is the value of m, suppose. Now, our universe is oscillating, like I am oscillating at some speed. How much energy I require? So if we calculate this energy which is required to accelerate the universe at the speed we are observing here, that requirement is very, very low. is compared to the theoretical value we are having. So we cannot deny from that calculations because the setup is different and the calculation and everything is different from where this calculation of theoretical value are coming. And we cannot deny about the observational value, the energy required to accelerate me for up to the some speed. So at their place, both things are accurate and there is no errors like that there, but the value is not matching. That is the problem. And I think
just to add on to that, that value is not matching, it's true. But one side says that vacuum has some non-zero net curvature. And the other side says that non-zero net curvature should be the vacuum energy. Yeah, but without any, I mean, why should you equate this to any? I have something with some curvature, it's fine. But why should I say that that is exactly the vacuum energy as produced by pair-antipair, particle-antiparticle pair creation? So it is subject to, once you add that, once you equate that, it's a problem. But if you keep them separate, it's not a problem. Anyway, I have a small comment to make. When you see, when you modify gravity to take care of this cosmological problem, there's definitely a way to do that, modification of gravity. But there are certain experimental facts related to gravity, which we know pretty well. Like if I drop an apple here, the acceleration will be 9.8 meters. Yeah. We know that perfectly. We exactly know how much the perihelion of Mercury is changing. We exactly know how much the light bends when it crosses to the sun. So all this comes from Newtonian, post-Newtonian, post-Newtonian things which are very well understood. Yeah. And the point is, whatever action you are changing up there, it's fine. If it is not giving me 9.8 meters per second square, then there is a trend.
Yeah, definitely.
So why I say that, because this has been going on for ages. Why did not take Brans-Dicke theory very seriously? Because when you use that theory in these sort of local experiments, that makes the parameter of the theory so constrained that with those constrained parameter, you don't get cosmological acceleration. So similarly, for any f of rt, there are papers on f of r which post-Newtonian calculations.
As you are talking about the Brans-Dicke theory there in phi, and
yeah, so there is a very, very rigorous constraint on phi. If you need to satisfy the perihelion of Mercury and
but the other way like that is the phi we are having maybe behaving like differently in the local place and behaving very
absolutely. That's where the chameleon theory comes in, which are one of our colleagues in university, Amanda Weltman, is famous for. But then for that you have to put another field which acts like chameleon. What does chameleon do? If a chameleon sits here, it will be brown. If it sits on the chair, it will be blue. So you can have, but again from air, you have to put another scalar field which acts like a chameleon. So there is no end to it. But that is the point. Any theory you make, that's fine. But it should actually give us the local constraint, which is very well understood.
That's we are all are doing that. Try to make some theories and explain the things more better way. If we are having problems with lambda set, let's try to find out some solution using the other way. And it is very, I think, it is not maybe possible to have single theory to explain everything or everything about the universe. Maybe the combination or mixture of some theories. We are doing that kind of stuff to look everywhere in the every direction there. You can find some better way to understand things.
Any other comment?
Well,
Suleiman?
the fine-tuning problem is linked to the renormalizability of GR. The number of constants available is too many compared to quantum field theory, which is normalizable. That's why we have a difference. So now what Swami is talking about is there's a problem with new theories. So the idea is to correct the theory, to make them compatible. Now each time you create a theory, you lose something, you gain something, and so on. But one thing we know for these theories that you mentioned, f of RT, restful, unimodular, f of q is now using in the market, f of g is using in the market, that's what they, our recent trend, Burma is f of gb is using in the market. Most of the experiments, our theory is done on the linear form of those things. All of these are equivalent to GR. That's well known, that's now known. And when it becomes equivalent to GR, then all your solar system tests will pass. All these things will work out very independent parts of Mercury. So then you'll be safe. But actually, you're not learning anything new because you're working in a version of GR actually. So this FRC, no, unimodular. Einstein proposed it to correct this same kind of problem. George Ellis recently, about 10 years ago, wrote a paper about how this discrepancy in that value of lambda goes away if you work with the trace figure. So there are ways to cure the problem without violating well-known effects.
So, let's thank the speaker again.